Good day everyone and welcome to another video lesson. In this session, we will explore the skill of sketching the graph of a rational function. We're calling the learning competency representing a rational function, domain, range, asymptotes, tables, and graph. At this point, please pause the video and read through the learning objectives. Let's recall, can we divide a number by 0? Clearly, the answer is no. In any particular rational function, what happens to the fraction when the denominator gets close to 0? To answer this, here is a quick real-world analogy. If a small denominator is like dividing a tiny piece, the result explodes. So let's have a very short numeric example. It's GeoGebra time, okay? So we're going to compute the following and observe the blow-up behavior. So we're going to compute 1 over 0.1, next 1 over 0.01, and the next one is 1 over 0.001. And let's observe the blow-up behavior. Alright, so first 1 divided by 0.1, then 1 over 0.01. So the number is 100 now. 1 divided by 0.001 is 1000. 1 divided by 0.001. So as the denominator gets closer to 0, the value is getting bigger and bigger. So just imagine if we have a very small number for the denominator, and in such a way that it approaches 0, we have a very big number. So there is indeed a blow up behavior, right? So let's just exhaust this one. Again, so it gets bigger and bigger, and then eventually somehow there's a sensation of blowing up. Therefore, we can say that as the denominator becomes very small, the values get very large, approaching the idea of positive infinity. Alright, so now we're going to find the domain. The first step in the graphing task is to find the domain. To find the domain of a rational function, we simply identify the value of x that would make the denominator equal to 0. So we have 3x plus 12 not equal to 0. By simple algebra, we obtain that x is not equal to -4. Hence, the domain is a set of all real numbers such that x is not equal to -4. A rational function is defined if and only if the denominator is not equal to 0. So this single excluded point indicates a vertical asymptote. Alright, so the next step in the graphing representation of the rational function is to identify and draw the vertical asymptote. First, we need to factor the numerator and denominator if possible. But in this example, the numerator 9x plus 2 does not share any factor with 3x plus 12. Therefore, the value x is equal to -4 makes the denominator 0 and gives a vertical asymptote. So we have to check the denominator becomes 0 at x is equal to -4. So the graph has a vertical asymptote at this value. Step number 3. For the third step, we determine and draw the horizontal asymptote. So here's the process. Look at the degree of both the numerator and denominator. In this case, both degrees is equal to 1. When the degrees are the same, we use the leading coefficients. Again, the horizontal asymptote is the value of y where the graph is heading as x approaches positive infinity and negative infinity. So what's the value of y when x is a very big number and when x is a very big small negative number? Okay, so the formula is y is equal to leading coefficient of numerator divided by leading coefficient of denominator. The leading coefficient of the numerator is 9, and the leading coefficient of the denominator is 3. 9 divided by 3 is 3. So the horizontal asymptote is y is equal to 3. So note, Again, when we have the same degree for the numerator and the denominator, in finding the horizontal asymptote, we just get the ratio of leading coefficients. Now, for the behavior near the vertical asymptote. So next, we observe and confirm the behavior of the graph near the vertical asymptote, x is equal to -4. The goal is to show the blow-up behavior as x approaches -4 from the left and from the right. When we say from the left, we begin with values such as -10 and move toward -4.1. When we say from the left, these are values less than -4. And when we say from the right, we start with values such as 2 and move toward -3.9. When we say from the right, these are values greater than -4. Here are the guiding questions for your observations. As x approaches -4 from the left, does f of x approaches positive infinity or negative infinity? And what happens when x approaches -4 from the right? So to answer these questions, we simply substitute the chosen x values directly into the function to compute the corresponding y values and complete the table. Alright, so here's a look at some of the data computations used when completing the table of values. We simply perform direct substitution. For example, if x is equal to -5, then f of -5 is equal to 9 times -5 plus 2 all over 3 times -5 plus 12. That would give us -45 plus 2 all over -15 plus 12. And now we have -43 divided by -3, that's equal to 1433. And then if x is equal to -4.5, we do direct substitution, the value of y is 25.65. And if x is equal to -4.1, then the value of y is 116.33. So these computations, we observe that f of x grows very large and positive as x approaches -4 from the left. Right, so here's a sample summary table. And now it's GeoGebra time. So let's take more values of x that are less than -4, but extremely close to -4, and observe how the value of y blows up toward positive infinity. So we're going to examine the following values: -4.001, -4.00001, -4.0001. Okay, so let's do that. Alright, so we type the function. And then we're just going to have f of -4.001. Okay, so right, so with -4.0001, this one, we have a very big number already here. And then let's have another value of x is very, very close to -4. So the value of y is extremely big already. So do you agree now that as x approaches -4 from the left, the value of y approaches positive infinity? Yes, indeed. So this confirms our earlier observation. Alright, and now we have a slider here. So as x from -5 approaches -4, okay, then the value of y becomes very, very big. See? It goes up and up and up there. Alright, so similarly, here are some of the data computations to complete the table of values for observing the behavior of y as x approaches -4 from the right. So for example, if x is equal to -3.9, slightly greater than -4, then the value of y is equal to -110.33. And here's a sample computation also when x is equal to -3.5. So again, we're just going to do direct substitution. Okay? So this expression produces a large negative value. Okay, so as we gradually complete the table of values, we observe that f of x becomes increasingly large in the negative direction as x approaches -4 from the right. Alright, so similarly, GeoGebra time. Here's the summary table, by the way. So using GeoGebra, let's examine more values of x that are very close to -4 from the right. Like for example, -3.999, -3.9999, and -3.9999. Okay, and let's observe what will happen. Alright, so we simply type here in our algebra pane f of -3.9999. Okay, it's a negative number, a big negative number, and then another value of x that will be very close to -4 from the right. Okay, another negative number, a very big negative number, and let's have another x value that is very close to -4 from the right, like this one. Okay, so the GeoGebra returned -infinity. So what do we notice? Yes, as x approaches -4 from the right, that's values greater than -4, the corresponding y values approach -infinity. Now, after determining the vertical asymptote and observing the behavior of the graph on both sides of it, we will confirm the horizontal asymptote is indeed y is equal to 3. We ask ourselves, as x becomes very large positive or very small negative, where does the graph approach? So this is the table of values we need to complete, and here are the guiding questions. So when x is equal to 100 or 1000, does f of x approach 3? And then do negative values of x approach 3? So we'll perform direct substitution to complete this table of values. Alright, so it's GeoGebra time, but before that, here's the table of values. So as you can see, from 0 to -1, the y values approaches 3. And then from 0 to 1000, the y values approach 3 as well. Alright, so let's have 1000, this value. What's the value of y? It's 3, approximately 3. And then it's still 3 here. Okay, how about negative? So negative, this small number, it approaches 3. F of negative this much, let's see, it's also approaching 3. Now, please answer the following guiding questions. Feel free to pause this video while you work on them. And so finally, here's our summary and our key takeaway. So domain restriction, x equal to -4, so that's our vertical asymptote. X is equal to -4. The degrees are equal, so in finding the horizontal asymptote, we take the ratio of the leading coefficients. So 9 divided by 3 is equal to 3. The table near asymptote confirms blow up, so the table with large x confirms approach to y is equal to 3. And we're going to ask all of you in your own words why y is equal to 3 might not be included in the range. This is because for any x value, the corresponding value of y for this function will never be exactly equal to 3. It only approaches 3 as x approaches positive infinity or negative infinity. So again, as you can see in GeoGebra, it does not say equal to 3, but approximately equal to 3.